Hey everyone, so far we have talked about many aspects of large language model, including the inference process end-to-end. We know that we can download models parameters from Hugging Face and then use it using transformers. Let's quickly look at how does it look like when you download the files locally. Okay, so once I download the file, it will save in this folder, and then I can look at the individual models. When I look at the snapshot, I will see these files are pulled down from this repository. As you can see, not all the files are downloaded over here. Only these model.save tensors, these parameter files are downloaded for the inference process in Hugging Face locally. All right. We also look at the scaling laws because we know in the case of GPT-2, 4 different models are trained and released and evaluated. Right. These just prove and validate the scaling law. Right. Like OpenAI have mentioned, based on these 3 diagrams, they just prove that the model's performance will increase when they increase the model size, data set size, and amount of computing used for training. Okay, this just give us a guidance on how we can scale the large language model to make it more and more powerful. But they also mentioned something very interesting over here. Is they say the performance depends very weakly on other architectural hyperparameters such as depth and width, right? But we also know that Chinese company DeepSeek, they did release their own DeepSeek model, right? Which they managed to achieve very high performance, but they use less computing budget, right? Not using tens of thousands of GPUs, but what they've done is make this architectural design innovation to get this good result. Okay, that's something interesting to notice. Again, recall that what really set Transformer apart from other deep learning neural network is its ability to capture these long-range dependencies and relationships between tokens using this attention mechanism, which is considered as a key innovation in transformer-based large language model. All right. Bear in mind that one of the factor that behind this effectiveness is this uh, highly parallelizable. All right. Because in the multi-head attention, you have several attention layers that running in parallel. Okay. As it also mentioned in its paper, saying this parallelizable requires significant less time to train. All right. This video, we will focus on the training process. There are multiple stages in training a large language model. Pre-training, supervised fine-tuning, and reinforcement learning from human feedback. Models are pre-trained on large raw dataset and then fine-tuned on smaller datasets for specific tasks. We can clearly see in GPT-2's technical paper, okay, GPT-2's technical paper, we can see in their training dataset, okay, they essentially did not use common crawl because they worry about their data quality issues, and they end up developing their own strategy to scrape web content, and then they end up getting this web text dataset. If we see the size, it's over 1 million documents, over 40 gigabytes. But bear in mind, this size is after they do the filtering, deduplication, and cleaning process. Okay. In terms of the diversity of the dataset, GPT-2 also release something over here. They say to get a sense of the data that went into GPT-2, they have published a list of the top 1,000 domain in the web text. Okay, the domain is just over here. We can see the top one is Google, and then it goes on and on. And this is the frequency, and this is the domain. Okay, although we do not get to see the full data set of the pre-training stage, GPT-2 does provide a partial data set for their web text. we can just download it over here, but this is not the full 8 GB. This is not the full 40 gigabyte of dataset. This is way smaller. Okay, there's some effort try to reproduce the dataset for web text. We can see over here in the Hugging Face, researchers from Brown University, they try to replicate the full web text dataset for OpenAI. Okay, if we scroll down, we can see how they do this specifically. First of all, they just extracting ready URLs, and then they do some deduplication and do some filtering on the non-HTML content and also non-English content. And then they do the downloading, and then they processing using the newspaper Python package. After that, they did another deduplication process. They use this strategy and then remove some additional data set that's very close to each other. And then after tokenization, they also removed very short documents. This give them this around 40 gigabyte, just over 8 million documents, which is exactly like this one. As a result, if we do want to pre-train a GPT-2 model from scratch, we can just use this piece of data set. Other than this, you can also use other open source replication of web text. For example, WebText 2, Open WebText 2 is an enhanced version of the original one, and it covers a longer time range until April 2020. They provide multiple versions, plug and play version, and also raw scripts version. They also include an code snippet you can use when you load their data. If we look at this background page, they also explain the original web text, how they get generated. And also, we see in their web page, you also can see this full data pipeline you can use to build the full data set from scratch. Okay, like we've mentioned before, in the case of GPT-2, they never publicly release their pre-training data set. Let's look at another case. In this technical paper for Meta, when they trained the Llama model series, they just mentioned that they only use publicly available data, make it truly open source. Okay, they also give us this table, which is a very good overview for us to look at the diverse and the distribution of the data set. All right. In this table, it just shows where are the data coming from, and also the sampling proportion and training epochs and disk size. Okay. In the paper, they also mentioned that they get inspired by the chinchilla scaling law. Okay. So let's quickly look at this scaling law. So this chinchilla scaling law, they just give us a better view about all three factors impacting scaling a large language model. Specifically, they just propose this optimal ratio of this training token and model parameters. They say 20 is this recommended way. Okay, what does it mean? It means if your number of parameter is 400 million, they recommend you to have like 20 times of this parameter size, which is 8 billion 8 billion tokens. Similarly, for 1 billion parameters model, you should probably have 20 billion token size. Okay, so this scaling law just help us to avoid overtrain or undertrain our model. Okay, if we look at this paper again, we can see the parameters and these training tokens, right? Very interesting. We see well, for example, in this model, is clearly overtrained, right? This is way more than the 20 times of the number of parameters, yeah, which is also a very interesting thing to notice. Okay, other than that, let's also have a look at the another popular data set, that's Fine Web. Okay, so in this case, the data size is 15 trillion token and 42 terabyte disk size. They also have another subset. It's called FineWeb EDU. Um, they just provide very high quality educational content. You can also download it. I highly recommend you guys to have a look at this blog post, especially this recipe, basically the FineWeb pipeline. Generally speaking, right, the purpose of this data pipeline is to give us a very high quality data set. They just cover from the collection to the cleaning and deduplication and multiple stages of filtering, removing certain unused PI data, and finally save in your storage and get ready for training. I guess other than this, the similar principle will apply to multilingual or other domain-specific dataset, and obviously multimodal data like image, audio, and video data. You also need to go through this process. If you ever want to include any proprietary dataset, you also need to consider other factors. For example, legal licensing, copyright, and other ethical considerations. Thanks for watching. See you next time.